Hello, everyone. Welcome to another Wolfram Language Design Review. We are talking about control and system modeling. We had a meeting about the same topic a little while ago. And Sergio, please tell us what you've done.
Can he share his screen or?
Prefer
Yeah.
not. I'd prefer not.
Oh, I
No,
guess we can then.
I mean, you could look at it, but you can't run it because it's not in today's prototype build.
Right. So you can
Okay.
go to the documentation then of system model surrogate train, and then
What is it called? Just
system model surrogate train.
That was definitely not what I wanted. I thought that was looking odd. I didn't think it was looking like my usual. Okay.
Right. So if you go to the first example,
Okay. Whoops, notebook is not scrolling properly.
It takes a while for the front end to initialize.
right. So yeah, so this is so in the photorized cell is the thing that is one of the things that you mentioned that you wanted surrogate to system model plot to be able to accept the surrogate directly.
Good. And it can.
Right. And we also made the progress reporting a little bit better, but I guess that's
Okay. But by the way, on that scroll thing, if that was initializing something, that should have had a spinner of some kind. Am I making sense?
right.
I don't know who sets the front end spinner, but
Yeah, well, so that's what I'm telling you. And that's what I'm telling you. And we have Tracy here project managing, so she can communicate that.
Yep, I will.
Okay. That looks nice. All right, what's next?
there's a few more things. So largely it can be used, the system model surrogate can be used in many places where you can do a system model simulate of it and generate interpolating functions for particular parameter values. So this
Okay, but we talked a bunch about parametric function and the possibility of a system model. Let's see, system model simulate returns a system model data object, correct? Or
Yes.
system model simulation data object.
Mm-hmm.
So we talked before about what should happen. I mean, with system model train, what does it return again? We talked about it. Go ahead.
It returns right now a system model surrogate.
Okay. And last time we talked about wrapping a surrogate around a surrogate. Is that right? Or what was the idea there? And how would you get out the thing that's a more plain function?
So one thing that you can do now is to actually simulate it like we do with models, because
Okay.
the surrogate also maintains parameter dependence. So if you set those parameter values like you would have to do for ND-solve, you can get something out that no longer allows you to vary the parameters.
Okay, I get it. So it makes sense to say simulate the surrogate model
It
and get
does.
from that a system model simulation data object.
Exactly.
Right.
Sounds good to me.
But we also want, for other use cases, we want the parameter variation. So I mean, it's really good to be able to get out a parametric functions where we can vary the parameter because we want to optimize the parameters. We do want to vary them. That's a richer object.
I get it. Right? It's both richer and poorer because it's just those particular parameters in some more mathematical form, right?
Right. I mean, the system model itself probably, typically allows you to vary many, many more parameters and has many, many more variables.
Okay. But now parametric function well, let's see. It could be an interpolating function. It could be a parametric function, right? But somehow,
Yeah, so the parametric function it's a curried form, right? So it takes parameters first and then t, it's like,
as opposed to an interpolating function, which just takes t.
yes.
But so what you're really trying to do is you're trying to take system model simulation data and you're trying to slice off, as you did here, a particular thing, right? You're trying to take a particular slice that is for example, a parametric function, correct?
Yeah, but the surrogate is more, simulation data is just like output from NDSOL. They're just sort of dead interpolating functions. You can't vary parameters anymore.
I see.
Do you know what I'm saying? Those are locked down when you do that.
But you can do a parametric function from a simulate, yes? Or at least an
No.
interpolating function.
Interpolating function, yes, just like NDSOL. Parametric NDSOL can return a parametric function where you maintain that parameter variation fast, and efficient.
Okay, but I mean, for example, I would imagine, given a system model surrogate,
Yes.
you want, let's say, parametric function or interpolating function, you might have 300 variables in the original thing, but you want to compress that down to just 2 variables.
Right.
For
That's
purposes.
Yeah.
Right. So how do you do that right now? What's the plan for how to
System model surrogate train. There you tell which parameters do you actually want to maintain in the surrogate.
But I thought that system model surrogate train returns a system model surrogate, does it not?
Yeah, which can be evaluated. And you.
Okay, but wait a second. Is the surrogate? Could I say I want a surrogate of everything?
You could, but it would not be realistic because it doesn't scale that well. I mean, you could say it, but it's not.
Okay, but so surrogate here is.
Surrogate is kind of like a replacement for the model. It's not a replacement for the solution.
Replacement for a subspace of the model.
Yes, typically, yes.
Okay. And how does it reflect? I mean, I have to say, I'm not wild. I mean, like something like this. It has no list of variables or anything.
It does.
I could imagine. What's that?
It does.
Well, I know, but it's not visible.
No, right.
But I could imagine that with a surrogate model, if you're displaying this iconography, that the surrogate model, if its variables that it's actually poking at, if it's actually connected to, involve, that, whatever that thing is, inductor. I don't know what that is.
Inertia.
Oh,
it's like a spinning mass.
Yeah. Okay. Fine. That resistor or inductor, whatever it is.
Inductor.
I can't see, it's wiggly. Okay. That thing, that spinning mass, if it might be nice on an icon like this for a system model surrogate to have the thing displayed as this thing, but with those things whose variables are actually, being sort of captured, highlighted in some way. Does that make any sense?
I don't think we have yeah, it's not super realistic. That would involve a lot of,
Would it be nice?
But the surrogate itself is not a system model. It's a net.
Yeah. But it's related to this one in some way, but it's derived from this one.
Right. But I mean, that would be clarity-wise, maybe in the documentation, you're picking out certain degrees of freedom from here, and you're making a model based on those degrees of freedom, right?
Mm-hmm.
Okay. So you've got some slice there, which is the system model surrogate. But the question is, then how do you go from that to something like a parametric function? Is that right? And what you're doing here is just have a sub-value.
Yeah.
Seems okay. I mean, it seems like a kind of thing for interoperability. It's going to be pretty common. Is you get the system model surrogate, and then you mainline it into an interpolating function, more or less.
If you simulate it, you can get an interpolating function. Because then you have to lock down the parameter values and things like that.
Okay, so the thing you get from it naturally is a parametric function.
Right. Because that's the goal. That's what we want.
Hmm.
I mean, you could just simulate the original one to get an interpolating function.
I see. I see.
And that the
Okay.
point is that there's some things you want to vary and still get a fast response. This is what this one is good
So
for.
the thing that I'm still wondering about is whether okay, so parametric function comes from parametric ND solve.
And a few other parametric things and future ones too.
Okay, but you're claiming it makes no sense that simulating a parametric model should return system model simulation data, which is not yet a parametric function, but which you can turn into a parametric function with a
No,
subvalue.
I think you missed the point. Oh, I see what you're saying. No, so simulation data, it's like the output from NDSolve. It's fully resolved into interpolating function. There is no parameter dependence at all.
Okay, it seems like there's a missing piece here, which is the thing that goes from the surrogate to the parametric function. Now you're doing that with a subvalue. The question is whether to promote that in some way. And I'm not seeing, I mean, the thing I'd suggested before is use the parametric function as a thing to convert from the surrogate model to a parametric function. But maybe that makes no sense.
Yeah.
Or use it as a wrapper.
Yeah. No. I think what we picked up on what you suggested, which were really good suggestions, I think, is that we can treat surrogate as an alternative to model. It's a simpler one, but you can simulate it and get just fully, interpolating functions. You can plot it for particular parameter values. You can do those things. I think that's useful because that means that you don't have to go that extra step to do it. So that clearly shortcuts a few workflows. That's always useful.
Sounds good. All right. Should we move on to the next section of the agenda?
Yeah.
I mean, let me just look at one thing here. I see. It's pretty fancy.
Yeah. It's pretty cool.
But I like the fact that it can go from a state space model and things like that as well.
Right. We've sort of systematically unified these so that almost all functions we have can now, in this space, can do that.
Just so I understand, I mean, naive question. If I have an electric circuit, what is the state space model does that make any sense to ask something like that?
Yeah, it does. But the problem is that there are many state space models. So, and that's what the typical course or, on electrical circuits does. It's trying to derive the differential equations and state space versions of those differential equations. And what you pick a state, you have some choices. So that's an art or its own.
What is a state for an electric circuit? What do you mean by a state?
Well, so
the configuration of voltages or something, or what?
Yeah. So the number of, for simple circuits, let's say it has inductors and capacitors. Those are active elements, which means that they store energy. So you can count the number of states you need as the number of such active elements, pretty much.
What is the meaning of a state in that context?
Okay. A state is just a set of variables that can describe a system. So
okay, that's what I kind of thought. So in an electric circuit, it could be currents, it could be voltages.
Yes. And you typically need both.
Right, but
But you can choose the voltage at one node as a state, or you can choose, say, voltages at two nodes as the two states. Or you can choose the states as the sum of those and some of those voltages and differences of those voltages. That's where all those combinations arise.
Right. Okay. Cool. All right. What else should I look at here?
I think that is it for the surrogate, and
it's cool.
More to come. Okay.
I'm sorry. What does the surrogate look like when you? Sorry, let me just see.
You looked at the net model? If you wanted to sort of see what it is as a neural net?
No, I meant what is its visual?
Oh. Mhm.
Is that bouncing? Is that real, or is that just an arbitrary icon?
That's arbitrary.
Maybe we could do better than that. I mean, to get across this idea that it is a system model, I don't know. I mean, that's just a very random picture. It'd be nice to.
So you have the name in front of it too that says system model surrogate.
I know. I'm just wondering what is the best communication we can have from that icon.
Right.
Any ideas here?
Um, so it's really like an infinite number of such solutions, right? One for each possible parameter combination.
Yeah.
Um,
But it's also something, I mean, okay, if it came from a state space model, there's no visual for that. I'm just wondering whether an icon even makes sense or whether it's just confusing. Because when I see that icon, I'm thinking, oh, great, my system is damping itself to whatever. But it might have nothing to do with it.
no, in this case, no.
Right. So unless the icon is purely iconic, some picture of
Maybe we should have something that more relates to the system rather than the solution, because this is still.
yeah, I think that would be good. Like an idealized version of my, put the taps in these places type thing.
That's too advanced. That's too much.
Okay.
But maybe we could have kind of a standard icon. I mean, it's not sort of because those diagrams or icons are pretty complicated, right? You can't have a little. I mean, that almost is too little on your left screen there.
Yeah.
That's a pretty small. And if you're trying to make that smaller, you can see.
Oh, I know, but we could have some idealized version of something like that.
Like, let's say we have an idealized gray version, but not
Yeah.
adapted to the system.
Yeah,
That
exactly.
will work. That will
Fine.
work. Let's
Okay.
try to get that.
But then clearly indicating that it's got, some aspects of the system are being sampled by having like taps in two places or something.
Yeah. But why do we say expression, by the way, Sergio? Isn't that? Oh, no.
Right.
So expression is the variable.
Mhm.
But why do we call it expression?
I think we just inherited that from
Where is it
other
called that? Sorry.
parametric
In the summary
function.
box. In the summary box.
Oh. That's really weird.
Right, I guess I could just say variables or variable.
Yeah, but this isn't parametric function here, right?
Right.
So we don't need to inherit from it.
Okay.
Okay. Looking nice. All right. Should we go on?
Yep. Then there's sort of
we're
two.
agreeing to call that net, right? We agreed to call that net.
That's also been implemented.
Okay, good.
So
okay.
then there are two
System
more
model, system
things.
model.
There's that, and then there's some control stuff based on reinforcement learning.
Okay. Humpful.
Did you update the documentation or no?
I did, yeah.
Okay. So, well, you get roughly the idea, right?
I don't think that calling this symbol, why don't we call it system model variable? Because that makes a lot more sense with this thing about having derivatives and God knows what else.
But they're not, okay, so we make a very distinct distinction between parameters and variables and stuff. Because variables change over time, parameters are constant over time in this context.
Yeah, but it's crazy to have symbol have a second argument that represents a derivative.
Yeah.
It's just weird.
I mean, it's not symbol, it's system model symbol.
I know, but it's still, What else could we call it? So variable, this is more general than variables.
Yeah, I mean, symbol is a little bit more basic because it can instantiate to lots of things, right? Variables, parameters.
I know, but what's an alternative to symbol or variable?
Expression.
Definitely not. You know, this entity construct, all those kinds of things, but none of those are good. What are these things called in Modelica?
So in Modelica, they're called variables and parameters. The ones that change over time are called variables.
Identifier is what you know, that's another term for these kinds of things.
Right.
If the derivative thing is important, without the derivative thing, system model symbol is just fine. What about system model? Sorry, what about system model object? Do we already use that for something?
We don't actually, but that sounds very general.
Which is good, isn't it?
I mean, usually an object is things that you can, like, I don't know, instantiate and have methods for, and, you know, something. This one is more like an accessor, you know. It's like a named accessor type thing.
But you know, the fact that it's got a derivative, it's a continuous variable with a derivative, it's not just an on-off switch and things like that. That's a lot of detail. And that's something goes way beyond it's just a symbol as an identifier.
Mm.
So how do we deal with that?
Yeah. Well, this was our attempt to deal with it. There's also indexed. So you can see the very first use case is kind of very close to symbol with a, you know, they have these dotted names that gets you into the naming hierarchy. But the following three are sort of things that we need to deal with too, if we're going to try to deal with it. I think that the first case is absolutely the most common, just the dotted names.
Okay. By the way, we need to talk about the print form here, okay, but what about the derivative version? Maybe it needs to be a separate function that does that.
But you need it as an accessor, right? That's how we use it, I think, Sergio.
Right, yes.
What does that mean? Explain.
I guess, well, one of the features that you can compute in System Modeler is sensitivities. So you could imagine this is stored also together with other variables in the simulation results.
Well, is it?
Yeah,
Or is it
yeah,
not?
Yes, it is, yeah.
Yeah, so the first derivative there takes in the derivative with respect to time, even though it doesn't say that. The second one takes a derivative with respect to a parameter.
I'm sorry, which one takes a derivative with respect to time?
The one that says der of c dot x. C dot x is a symbol, and it's the.
Well,
it's
why
the
aren't you using some crazy notation for that last one as well? If DER represents a derivative, you can put any old random crud into that thing, you know,
right.
C.x/C.p. Then we're fine.
Well, then we can do that. Isn't there a sense thing or something like
Yeah,
that?
there is a, so if you go, right, if you look,
It doesn't matter actually. We could call it whatever we want in a way.
right.
But I think that there is a notation that is like dir, it's called sense.
Yeah,
we
so
could-
it-
It
Yeah.
would be the same kind of thing as
Okay,
dir.
I
then.
must admit that my preference would be to have, you know, I mean, my preference would be to have system model parameter, system model variable,
Mhm.
system model derivative, system model sensitivity, or something. Or maybe just system model derivative. I just think, you know, these are, and, you know, maybe we have some autocomplete mechanism that makes these or something like that. I mean, why are we shoehorning everything into this thing? I think that you've identified a real difference between variables and parameters for your purposes.
Mhm.
And I think, why not capture that at a higher level? That's my recommendation. I mean, I don't think, I mean, unless there's some other wacky syntax you want to support.
well, not that I'm aware of. This is all coming from Modelica, effectively. It's
Right, but I would even say in your C.X there, I would say system model variable. You know, let's say either C arrow X or C, that this is an alternative.
there'll be many dots. They're usually long, many, potentially many dots.
Yeah, okay. So it's either this, so it might be C dot.
C1 dot,
list.
C2 dot, C3 dot, and then dot X.
Yeah. Okay, which you can also write out as, you know, because I think this would give one a fighting chance of some kind of computational, you know, you can also write it like that. Maybe its canonical form is this. So you can actually do things like use pattern matching, you know, use cases and things on it. Seems like it would be useful.
I mean, the full form already looks like that. If you look at the full form of the
So if I
system model
say-
symbol.
Full form of what?
Of system model symbol, yeah.
Full form. Okay.
Great. Why didn't you document it? Up here
Okay.
or anywhere else? That seems exactly right. So I recommend parameter variable, either sensitivity or derivative. Your comments.
I guess one of the challenges that we want to tackle with this is also that we want people to be able to type this easily.
No. You're off the game. You're out of the game then. Nope. This is how we represent these concepts. Okay. Typability is a completely separate issue.
Okay.
And the point, it's not going to help you. It's no more characters to type.
We can try that,
So-
Stephen. We're gonna have to go back. I can't immediately tell what all the interactions are. So I think we're gonna have to spend some time working through that.
Right. So I would recommend, in terms of typability, if you want these things to be typed quickly, I would recommend some kind of $escape something or other. I don't know what the system prefix is. You can have, I don't know, tilde, exclamation mark, whatever you want. Okay.
Mhm.
You know, something like that. If you want typability.
Let
Does
us
that make sense?
try to work it through. I'm pretty sure that this is gonna have to be 15.1 now, but we can work through it one more round.
Well, okay. That's unfortunate. I think it'd be really good to get this in now.
Yeah, but I don't think it's possible.
think it through. I think it's.
No, we
I'm
will
not-
think it through, but Sergio's gone, tomorrow or something like that. And then we are back into January. Then we're going to want to ship.
That's your problem.
Yeah,
Not the way
but
it
that,
should be. It's not the way it should be. This is something we should try to get into 15.0.
I don't think it's that important. We'll get it in, but it's not that urgent. It won't change anybody's life. But we'll work it through for sure.
The other thing you could do is consider hooking it into control equals, possibly. I don't know if that makes sense.
Yeah, that takes another investigation.
Yeah, I know it does. I also don't think the visuals of this are right.
Okay.
Okay.
So could you, so we wanted it to not be too long of a display.
No, I understand that.
So the tool tipping is, giving you the
I
full.
understand. So is the C relevant or not?
It's important because you often have, like
Okay,
say you
but
have a
this is
circuit.
If this was really C,
Hmm.
then it would be, as short as the ... You see what I'm saying?
Oh, no, they're never short to see. That's just what we
Okay, so that's just a fake.
Yeah,
so
that's
then-
just a fake.
Okay, so let's look at something more.
Look at that one there, inertia2.w. So that's a typical, more of a typical. Or
Okay,
resistor1.r.
Can I get a list in this thing? Can I just get a list of what all the variables?
Yeah. If you
Right.
get that model, you could ask for
System variables.
string system there. Yeah. And then you can ask for parameters too.
That looks a hell of a lot nicer than it did before, but how do I get the string versions?
You can do to string.
It's a pity to not have any information here, inductor versus whatever else.
Mm-hmm.
I mean, what we do in entities. Oh, for God's sake, does this not work in this version?
No.
I'm confused here. There's a different form for input and output, which, by the way, is another issue for you guys. Right, for control equals, I don't know whether okay, so we have this little thing that says species specification here. Now on output, it goes away. Do you see what I'm saying?
Mm-hmm.
I don't know whether that makes sense for you guys, but that might be a possible thing to do. I think if I copy this into input again, oh, that's strange, actually. I don't know why it does that. I mean, that was thought through in great detail.
Okay. Who knows about this, how this mechanism works?
Like James Melnix would know.
Okay. Could you take a note, Sergio?
Yep.
Okay. Let's just think for a second here. So you'd like to somehow have, I mean, what would you like to communicate here? I mean, these things, certainly if you have an equation, you do not want to have spring damper 1.phi.rel underscore rel everywhere in the equation, right?
Right.
Really what you want, if there's a single variable that's reported many times, you want some kind of legend for it. That'll be the best thing. Am I making sense?
Right.
So how would we do that? We could imagine doing that. I mean, we could imagine doing that as some kind of, I don't know. I mean, like what would be the best thing for us to do? And then we can figure out what the easy thing for us to do is. The best thing, it seems to me, is we're saying, you know, I, phi, whatever, where I is constant voltage 1 dot I or something. Does that make sense or not?
Do you mean like a full substitution of the?
What?
Do you mean like substituting the variables for something simpler?
No, that's not what I mean. How do I get the equations out of this?
System equations.
You're not going to like them.
No, I know they're horrible looking. Well, they're going to look a little better. Oh, look, they look a lot better now than they did before. But they looked terrible before. With these giant long things, they were absolutely incomprehensible. On the
Mhm.
other hand, I could see roughly what, you know, like this, like what the heck's going on here?
Mhm.
There's 4 phis that are. What is the best way to do this? What would be the best way to do this?
Maybe the same symbol should have the same color, and they should be differentiated by, so you can see the same symbol appearing visually in different places.
Right.
fast.
So what that would be like if we say generate asymmetric key pair. See these things here? Those are representations of the underlying keys. Cryptographically obscured in our case, but that is a possibility that each within, you know, that each one of those prefixes gets a different color, and we pick the colors essentially, you know, we pick the colors by a hash of that name. Do you see what I'm saying?
I see.
I think that will be worth trying. And then no dots, because that's just confusing to everybody. It would just be the last element. Now, I mean, this is going to be ugly. T underscore heat port. It's just nothing to do about it. I mean, it's just.
Yeah, we have, I mean, that's what users use, so to speak.
Now, we could format T underscore as the subscript, which might be nice. Right? Does that make sense?
Yeah.
Yeah, I guess unfortunately they can have several underscores.
It's all right. Just it's a subscript for the subscript. We're able to do that. Okay. So is there anything better we could imagine doing? I mean, the color coding is a good idea. Another possibility would be a glyph. I mean, is it useful to represent this? You know, on the one hand, it's useful to know it's a spring. On the other hand, it's useful to know that this variable goes with this other variable, right?
Yeah.
So which is the more important thing?
And yeah, so globally dereferencing, and we need full context, obviously. But, and thirdly, we spent some time thinking about that. Which use case do you need to know the global dereferencing? And which case do you want to know sort of what the end name is? To point to things, we need the fully qualified name. There's no question.
Right, but that's easy. We know that.
Right, right,
It's a
right.
question of print forms.
Yeah. And
Look, I've got
The-
another suggestion.
the context, as you can tell there, it sort of tells you like inductor 1.n.v. It tells you that's pretty much a voltage for an inductor, the N port of an inductor. That's the P port of an inductor.
I think it's worth experimenting with some kind of thing where you write that somehow very small.
Where? I mean, the whole thing? I mean, or
No,
above it?
no. And then
Oh,
I don't
B
know.
and
Above it's probably not going to work. Or you have a small space above where you can, for example, go C con ... age. That's probably not very useful.
We tried some of that. Couldn't. It's
Okay. Well, it'd be interesting to see what this would look like if instead of ... dots. Okay, here's another point. Actually, this is a not totally bad idea. Okay, so imagine if you did this. You break at every, both at every cameling and at every dot. So that becomes a blob followed by, in big letters, the, you know, whatever it is, the V or whatever. See what I'm saying?
Mhm.
I think that might work. See, so in other words, you're stacking, you're trying to make the thing square. And whatever it takes to make it square. Am I making sense?
Okay.
Look,
Well, we can
I mean,
certainly program it.
yeah, I know. So I'm if you take this, for example, anybody know how to split it at a cameling?
Hmm.
I think it would be.
Just do regular expression A to Z.
Is it A brackets AZ? No,
Yeah,
what is it?
capital A.
No, you want the lowercase
Oh,
first,
you want
then the
lower. Okay,
uppercase.
yeah.
Which is it? Is it A to Z like this? Do we do
Yeah.
that?
Mhm.
Okay. And then it's capital A to Z. And then we could try. I'd be amazed if this works, but let's try it. Can we do the split to both of those? Well, close enough. I don't know, how do we get it to not lose those letters? Okay, you guys can figure that out. But what I'm imagining here is that we have, okay, so then this is, can somebody help me out with this code, please? What am I doing wrong?
Non-atomic.
String split.
Mm. Do you want
Do
to
you
put the
understand that this
pillars?
is it's getting this? Let's not be too helpless here.
I think it should be in a list. The most is coming.
Right.
But it is in a list. String split is a list.
But it's picking.
Oh, it's much simpler. This is not completely crazy, in my opinion. That making sense to you guys?
Yeah.
I think with a nice, you know, that's not gray. We don't want gray. This isn't quite right, and we want to round the corners and so on. Only
Maybe if
obviously
there are a
the
lot of
stat-
levels, we just show
yeah,
ellipses.
yeah. We just show the beginning and end with some kind of dot there. This is going to work, in my opinion, because, and I think some color coding might be useful as well, because the whole point is that you're going to be able to pick up the visual shape of this prefix. See what I'm saying?
Mm-hmm.
Mm-hmm.
This is going to be nice. We can make it work. Okay, you'll need somebody from graphic design to finish that. Okay, let's go to the next item. Unless the more you can get this, the more you can succeed in getting this in, the happier I will be. Just going to say that.
Right.
I think it's more important than you imagine in terms of making this system more integrated and less like alien. Okay.
So what this is, it allows you to, it uses reinforcement learning to design a controller. And the specification for the kind of controller you want is one that minimizes a quadratic norm functions. If you go up and look there, the goal for that reinforcement learning thing is to ultimately minimize the sum of squares of the state and the input. And so the difference between what we have before and this is that you don't normally, for control design, you always need a mathematical model. And this can do with a non-mathematical model, just a computational model, so so-called environment.
Mm-hmm.
And so the actor, queries, it proposes some kind of input and it see what the environment reacts with. And the things that, so do you see that thing that's called J there? That's the global thing that you want to minimize. Okay. But the thing you look in reinforcement learning, you get sort of a local measure for every time you send it an input. That's that Q thing that you see next. See what I'm saying? Like in reinforcement
I'm
learning.
pretty lost. Okay, let's start from the beginning.
Okay.
Okay. We've got, okay, so first question. What other functions do we have that implement different sort of policies for reinforcement learning?
None. But we do have one that implement controllers. We have several functions that implement controllers.
Okay. And walk me through feedback control versus reinforcement learning, etc.
Okay. So in some sense, they are the same thing. So there is a type of control that's trying to solve this type of, it's called optimal control. And that's when you set the overall goal for what the controller should achieve is some some objective functions that you want to minimize. In reinforcement learning, you have similar thing. You have a value thing, reward that you want to maximize. You know, like what you want this system as a whole to achieve. Like say, if you have something that plays a game.
Yeah, right. You want to get it to win.
Yeah, that's the ultimate goal. But you might have, you know, for reinforcement learning, you need like a local goal too. Like at every step of the way, if you play chess and if you lose a piece, that's clearly like a negative.
Yes.
Right. Okay. So you get the local value function as well. And maybe you have some way of evaluating the state. And so it's complicated to come up with these local functions, these value functions actually for reinforcement learning.
Okay. But given, okay, so.
But what this one does is, you know, so control, if you scroll back up, I can sort of, so if you scroll in the reference page back up. Okay, we have another fun. See that J there just below the first illustration? J equals basically the 2 norm, a weighted 2 norm of the X, and the U, and there's a cross term. And that's essentially like a 2 norm. It's like a quadratic criteria, right? It's a sum of squares. And so you want, you know, it is kind of like the energy in both the X is the state and the U is and the input. So you want to minimize the energy in the state and input. That's kind of like your overall goal. Don't use too much control action and don't let the state get too wild, basically. Okay, as you could imagine, like it's bad usually.
Yeah, I understand.
Okay, so we have other functions. So LQ regulator gain uses that very same goal, that same J, and uses a direct, more mathematical type algorithm if it has a mathematical model of what the environment is. But now with this function, we don't need a mathematical model of the environment. We need a function that can simulate it. That's all we need. That's the main thing that this one does.
We've had system model controller data before, right? That's what.
Yes, yeah. So it's something we already have. You know, because in this case, it will return something that can be represented in that, no problem.
I don't understand how this has enough information to train the regulator.
Yeah, this thing that says input model here, which is the environment, that just literally says what the state update function is. You know, given a state, which is #1, given an input, which is #2, this thing computes the updated state.
Surely it should not be called input model. Surely it should be called something like input model function or something.
Yeah, probably.
It can be a function, it can be a model, it can be a system model. So that's why, and that's the name we've been using.
I see.
Yeah. It can be a C function, it can be a C code.
I mean, it's literally in Wolfram language, it is a function. Whether
Please
that's
don't use this plot ops thing. Just use opts. Don't use the lowercase uppercase convention here.
Okay.
It's pretty fancy. Can I see a more real example?
Yeah, if you go to the application section, I don't think we have as much as cool applications as we want yet. We've gotten it all to work, but we're just now kind of putting all the better application.
So in this one, yeah, so I'm building up the library first. Just showing a simple example. Yeah, the first code is just building up the environment.
By the way, if we're serious about continuing to support this C stuff, we should review it some more.
Yeah,
you know,
we should.
In modern times, we could bundle a compiler. It isn't very difficult.
Yeah.
Can we get that onto GPL, and can we, get a review of this, please?
Yep.
I mean, this isn't going away.
This is mainly to make it self-contained, so it's there. But let's say that you have a lump of C code that simulates your system.
Yes, but I mean the level of messiness here is rather.
Yeah, just setting up the library initially.
Yeah, it's just too high. I mean, why aren't you using the foreign function interface with system
Yeah,
binding?
we're
He
using
does.
the
We do that. That's there too.
so we're
Okay.
showing an example both with foreign function, also with library function.
Let's clean up this C code thing so that we can end up with a thing that plugs right into the foreign function interface and so on.
Yeah, so this is the foreign function.
My God. Okay, but this thing, this model is always taking current state.
Yeah, it's giving it just, yeah. It takes the input state and then returns the new state.
And this just automatically trains it in some.
Yep.
I'm very confused. Where is the objective function?
The second argument.
Second argument gives those Q and R matrices that are sort of the weights used for that two norm.
Okay.
That tells you how much you weigh state being small versus input being small, basically, or which ones components of those need to be, how they relate to each other.
I should understand this better. This is interesting. How well does it work in practice doing these kinds of things?
This actually works pretty well. There's a sort of an assumption here, which is that the underlying system, even though we don't have a mathematical model of it, behaves linearly or not too non-linearly.
Mm-hmm.
Okay, so there's still some assumption. And if you violate that assumption, it probably won't converge. You can have surprises.
Sorry, say that again.
If your system, your environment, if your environment does not behave like a linear system, or it's, if it's close to a linear system, it's probably okay. But if it's wildly different, this is probably not going to converge, I'm assuming.
Yeah.
Yeah, I think that's basically it.
So, for example, these things that I've been doing with biological evolution, where you tweak. I mean, one of the things you have to be able to, you're taking derivatives here, is that right? The model, somehow you're differentiating. How are you making the moves?
It's a difference equation, basically. So it just that state or that function gives given state and input, it gives you the new state. That's essentially
okay, but if it's C code, how does it? I don't understand what.
Yeah, you can see the C code there because I've written the C. It's very simple in the examples in the scope.
No, but I understand. But this wrapper, system model controller data.
It contains almost nothing. Okay, it's just a simple. The end result here is a gain. It's like a vector. So you're going to dot it with your state. That's what your feedback law is. It's super simple in this case. It's not like a whole neural net.
And then you feed that in as the state, and then the model determines the next value. Is that correct?
Yes.
Yeah. So when you want to implement it, deploy it in the real world, you get the state out from your system, dot it with your gain vector that you've computed here, and feed it back in. That's how the controller works.
Okay. So in other words, you're effectively taking a filtered version of what you observe for the system, and then you're feeding it into this update function. Is that right?
Yeah, there are two things. Okay, the environment is an update function. It simulates your environment.
I got it.
Okay. The controller is also, if you kind of like, it's also an update function because it gets at every sample, it will get a new state, and it says, okay, I'm going to generate a new input for you. So like I'm dotted with my K vector, and here's the new inputs that I want to generate, and you feed it to it, and you just keep doing that in a feedback loop forever, basically, as long as you're running your system. That's how controllers work generally. And that's how this one works as well.
So what, just for my education, I mean, this is an LQ regulator. What are the other things in the world?
Okay, so this one is, so this is linear quadratic. So, and it's called that because it's like underlying a linear system and it's a quadratic objective function.
I see.
Okay. Now there's a gazillion ways to design a controller. I'm sure you've heard of some, like a PID controller and
Yes.
other things. What we hope to do here as we evolve the reinforcement learning side is to take on wilder kinds of systems. And we haven't decided exactly where to go with that yet. But for instance, you could imagine systems that have a discrete component, like a mode or something like that. Now, calculus and numerical mathematics doesn't really work with that particularly well.
Mm-hmm.
So that's very hard to do with control formalisms today.
So what happens with PID controllers? How do I get a PID controller relative to how I get an LQ control regulator?
So you see that the input there for a PID tune is a system. And the system is what we call environment.
That's a pink box that says failed in this
Okay, I thought I fixed it, but yeah, I'll look into that again.
Okay.
So the way it says sys, that's your system that you're going to control.
Mm-hmm.
You know, that's what's called environment in reinforcement learning terms.
Mm-hmm.
So given that environment, this thing will figure out the controller for you. And then you have a few more things that you can specify as exactly how and what and this and that. This one that the PID tune, what it does is not unlike what a reinforcement learning system does, because it effectively will identify like a little simple model of how your system behaves. And then it will use that simple model to design your PID controller. That's how it
almost like a surrogate model.
Almost like, actually, Stephen, it is effectively like a surrogate model. It's a very sort of mathematical type surrogate model that turns out to work really well in this case.
Mm-hmm.
Yeah.
But then I don't understand the relationship here between, if I say PID tune and I put in one of these things that we had earlier on here, what will happen? Is it just to go bonkers, or what does it do?
No, it will work. So
it will work, yeah. It will.
It's supposed to. It depends if it's stable, if it can handle it.
We need to know what. Okay, so that's what it needs to do. So when it's nonlinear, it will try to linearize.
Okay.
It couldn't linearize. So if it could so the difference between these traditional control techniques and this new reinforcement learning is the traditional control technique, as you see there, it's looking for that linear model. It wants an explicit model. So it's when it sees a system model, it immediately calls system model linearize. And then it gets that linear model. It uses those values of that model. And then the control design is based on those explicit values.
I see.
Whereas for this new function, the new function LQ regulator train doesn't know the internals of the model. It only sends the input and gets the out and gets the new state. And the controller is being developed based on those values. That's the fundamental difference between what we had earlier and this new function.
When you say Q learning, I mean, people talk about that in connection with training LLMs and things.
Yeah.
What does the Q stand for here?
The same. It's the same thing. It's called the Q. It's called the Q function or the action value function. So that's how this.
Is that learning. The quadratic? Is that the thing which is quadratic or?
Nope. This Q. The Q learning is a term from reinforcement learning.
I'm sorry.
Yeah, this actually should. To be fully correct, this Q learning should actually be capital Q, just to not mix it with the Q that we already have there.
Okay, but what does it mean? What does that Q mean?
Yeah, so in reinforcement learning, they have this concept called the action value function, which I explain in that. If you open that ref page for LQ regulator train,
I'm going to have to run here real soon.
Yeah, see, I say in that just below that illustration, and that quadratic cost, I say that using the Q function, and that the Q function, yeah. It's called the action value
quality function. Yeah. Q for quality.
And that's that's what this algorithm is based on, the LQ regulator train.
Okay, can you explain to me, and I'm late for another meeting, but
It's not the same thing, it's related. So I talked with Julia about that.
Okay.
And so the active classification, what that's trying to do is trying to figure out, let's say that you're gonna drill for oil or something.
Right.
Okay. Is it worth, you have something that
Yeah.
allows you to gauge like how much more information can you get by getting another data point at a certain location, let's say. And that's what active means here. It's a way to save resources when they're expensive. That's what
Whereas
active.
here, you're really using calculus at some level.
Yes.
What? Just so I'm sorry, for a PID controller, that's something integrated. What does that do? What is it?
What PID stands for?
Mm-hmm.
Proportional integral derivative. And so if you look on that ref page, if you just sort of a naive and actually pretty good way to do a controller is to just, let's say that you wanted constant temperature in your house.
Mm-hmm.
So let's say that you formed the difference between what is your desired temperature and what the actual temperature is.
Mm-hmm.
And let's say that you adjust the temperature proportional to that difference. So you can go negative and positive.
Okay.
But then you can never get it to be zero. The difference can never be zero.
Right. So you
But if you
integrate it over some reason.
then you integrate over time and you can get it to be zero. If you can have derivative, then you can kind of look ahead and anticipate things too.
Yeah, in
Right.
that second cell there, you see the structure of that controller. That's where its name comes from.
Right. And so what's the analogous model here?
There is none.
So this system here is the system there. Yeah, the regulator is, so the regulator or agent that is a block here, that is the GFB in PID. If you want to like compare the two. The sys there, the system there is the sys here, and GFB is the regulator or agent here. Or if you, yeah, it's a loose
Okay, but
comparison.
what is the ultimate, a PID controller, I understand, sort of mathematical based on the input data.
Mhm.
Here, and I think you've been explaining this and I haven't been understanding, what is the analogous thing here to that mathematical operation?
Well, it's you're doing kind of a local action every time step. Like I said, you dot it, proportional to your state. But it's not formulated directly in the same signal, so that's why it's a little bit hard to compare because this uses the state. But bottom line is it's trying to that feedback law. If you
But isn't there
Okay.
some derivative somewhere here? You've got this thing that is how far
well,
away
it could
are
be
you?
it could be that the state encodes what's effectively a derivative. Okay.
Yes.
So the state can encode those things. And if you then just do something that's proportional to that, you get a derivative term. Or
Yeah,
the state that does an integral. And then if you dot with that, then you get sort of an integral term. So you can achieve all the same things with state feedback as you can with these PIDs and so on. For sure.
Okay.
Actually more things.
yes,
Well, this looks interesting. All right. I mean, I'm still trying to kind of bring it down to so just
so
another
to explain
question.
that again, to just add to what Roger said. So the states, right? As we did, the states could be like the position, velocity. So that is like the position and the velocity are like the proportional and the derivative terms.
Yes.
Yeah. So that's how the comparison happens.
Okay. So where are LQ regulators used?
Almost every, it's like a super common way to design controllers. There are these really simple ones like PID, things are stable, it's pretty simple. But when you get a little bit more sophisticated, you usually go to LQ.
So like
control.
a flight controller for a drone. Is it an LQ controller or is it something
Probably,
still
most likely an
fancy?
LQ.
Yeah, we have now a lot of examples in that LQ regulator page too, which shows a lot of
Right.
applications. Not here in LQ regulator gains.
Yeah, actually, you can see a ton of examples there. LQ regulator gains.
But so what does one go to if one's, landing a giant rocket or something? And I mean, what's the next level up from an LQ regulator?
LQ, then LQG, MPC. There are different techniques that people use.
So LQG, what that does, it also models things that can generate disturbances for your system. That's what G is, a Gaussian process. So let's say that you have, for a rocket, let's say that you have things that you don't model precisely, like wind.
Yeah.
Okay. So let's say that you have something that acts on your system, like wind.
Mhm.
But you have some kind of model how big those disturbances can be. That's what you model in that Gaussian process. Now you can build something that is able to reject those disturbances. You know, like your cruise controller in your car. Like if it blows on your car is probably still able to reject those things and keep the speed pretty constant. Or let's say it gets cold outside your house, you know,
Mhm.
things that are not modeled per se, but more
Well, I
like
thought a
noise.
PID controller would deal with keeping constant thermostat temperature.
It does, yes.
It does, yeah.
But
But it doesn't have a, you know, in LQ and LQG, you have a sort of an explicit model for how big or how bad those disturbances can be, basically.
Mhm.
So then, yeah, then you can tell it's sort of how fast should it reject those things, and
Yeah, they're just different methods. You can think of them as different methods. People could
Yeah.
use one versus the other. Yeah, so
Right.
in PID2, there are different techniques, and some of them are better at rejecting errors. Some of them are better at tracking.
I see.
Yeah.
So how will somebody deploy this? So they get this thing, the result
you-
is a model.
So the things that we've generated up to now, and including this release, we can generate for the microcontroller kit, for instance. We can auto-generate C code there's a runtime environment there
Mhm.
for those microcontrollers. That's a typical way for an embedded system, because you're not going to have a big runtime on a drone or something like that,
Mhm.
or in a car.
Yeah, so that's one of the advantages. So that's why we worked on the workflow. So now we return the systems model controller data object. So in all these traditional controllers, it returns the controller model. So that's why we show in that dashed boxes. So you can just take the controller model and then deploy it to a microcontroller or
Right. This is pretty nice. Let's hope people can actually use it. Looks good. I'd like
Good.
to understand it even more, but I think it looks good. Roger, do you have any further comments here?
Not really, but I think that in these cases, we're at the beginning of a journey here where we're using a lot of more these machine learning methods, both to generate a surrogate model and in here to do a controller design based on reinforcement learning.
So in the end, there's a neural net inside.
Actually, in this case, it's not even a neural net. It's just a K vector. In general, in the future here, we'll get basically a neural net inside.
So yeah, so there's different way we can do that. Agent here is just a quadratic polynomial. Yeah, but we could do a neural network that'll
Is
be
that just so I understand? I mean, in control theory in general, are neural nets the future of that? I mean, is that a new generation of
I think
control
that
theory?
I think that the jury is out. I think that it's still being proved out. And I think that one case, so there's a couple of cases I think are really interesting. One case, which I like to explore, but I don't know which order we do things. So let's say that you have, let's say, image sensors that gives
Yes.
you basically a video feed in. So you
Yep.
want to get a video feed in and you want to get control actions out.
Yep.
That would be a huge neural network. So normally that's otherwise, historically, that was done as separate processes. It was something that did the sensing and the data reduction to something that these mathematical models could handle, and then you do traditional control. But one thing that we've seen, and Tesla and others are using, is that you kind of have a net all the way. So you do the video reductions from
Yes.
gigabytes per second to kilobytes per second,
Yes.
effectively.
Like brains.
Like brains, exactly.
Yeah.
So that's interesting, these modalities, particularly now that we get image sensors in places. That's one. And the other thing that I mentioned, dealing with sort of non-numeric data, like modes and discrete stuff like that.
Yes.
Yeah,
I mean, this seems interesting. It seems like it's something where, we can expect to merge a bunch of things we've done in machine learning with this.
Yeah,
Mm,
so we have this ongoing discussion with the machine learning team because we gonna pursue this. You know, I think that we have a way here to sort of auto-generate environments, among other things, which is also because it's like data processing without data is not so interesting.
Yeah.
And reinforcement learning without environment models is just not that interesting. So environment model is a big limiting factor among other things in this
Yeah.
space.
Sounds good. All right.
Okay.
Anything else for us to cover here?
No, I'm in
Good.
deep
Okay.
trouble. Thank you.
Good work. Okay.